one more sponsor plug before I introduce this next chat. Tracebit deploys cloud canaries or honeypots for intrusion detection. They've built something quite novel in this that leverages Terraform to scatter interesting resources. Think S3 buckets, IAM roles, secrets manager secrets around your accounts to catch bad actors. Our next speaker, Ian Mckay, in a talk, Hacking Clouds Using the Power of the Sun. Everyone, welcome.
Hi everyone, and thanks for coming to my talk, Hacking Clouds Using the Power of the Sun. My name's Ian Mckay. I'm from Sydney, Australia. I'm the cloud principal at a company called Kablamo, and I'm also an AWS community hero and ambassador. Before I get started today, I'd like to call out a couple of inspiration for my talk. The first is Artem Dyneberg. Artem did a lot of the foundational research in this sort of topic area all the way back in DEF CON 19. That's actually 12 years ago. The other person I want to call out is Ben Kehoe. Ben Kehoe told me a story the day before last year's for CardSec and really gave me the ideas and let me put it together such that I could create some of this talk today. Before we get into the meat of it, I do need to give a bit of a primer on the cloud authentication for the three main cloud providers we'll be talking about today. Starting off with AWS. For those who don't know, AWS technically uses this SigV4 process. Basically, you have an AWS access key ID and a secret access key, which are effectively a public and a private key. When you send requests, you sign those requests with your secret key, and then that goes over the wire, only containing your access key ID. Notably here, the requests don't include the AWS access secret access key. Now that's different to something like Azure, where Azure uses the OAuth 2 flow, especially when you're using something like Entra ID. The access token is passed alongside the request, alongside the body and the content of the actual request that you're making. These tokens may or may not be scoped down. There is technically a shared key flow, which uses a SigV4 style process, but it's only scoped down to specific services like the storage and batch API services. This is very similar to the way that Google Cloud works. So again, it uses an OAuth 2 style flow. Tokens may or may not be scoped down. There is technically a HMAC signed API style. If you want more information about that, Kat Traxler just published a blog post on this exact topic. And Google has one more authentication mechanism, which is the long-lived API keys. And that's basically, as you would expect, it goes alongside the request in the authorization header, like any other key. So why the sun? Why have I lured you in here today with my clickbait title? So now I have to talk about solar flares and cosmic rays. For those who don't know, solar flares and cosmic rays can be produced by the sun. Cosmic rays also coming from outer space. And this can produce a large amount of radiation into our Earth's atmosphere. Under certain circumstances, which are very rare, but common enough that you would experience it, these can generate tiny electrical charges. Now, this is actually really important because computer memory devices like RAM also stores its memory as tiny electrical charges. Now, when these two things interact in this very rare circumstance, it can cause what's known as a single event upset or a bit flip. That means a 1 turns to a 0 or a 0 turns to a 1. Let me talk about some of the examples that this has actually happened in the real world. In 2003, there was a Belgium election and they were using electronic voting machines. When they tallied the results, there was an unreconciled extra 4,096 votes for a single candidate. They did a complete hardware test, and that number is recognizable to some of you. They did a complete hardware test, and they found no issues with the actual hardware itself. And they actually narrowed it down to one of these single event upset events. This can also cause corruption in things like medical devices. A passenger on an airline actually had a problem with their pacemaker in that it increased to a rate of 70 beats per minute at an increased intensity. What had actually happened is that the onboard memory for their pacemaker had corrupted and it went into this fallback mechanism. Luckily, they were able to land, go to hospital, and effectively have their pacemaker factory reset in hospital. This can also cause corruption in airline systems themselves. In 2008, there was a Qantas flight that suddenly had a corruption with their angle of attack sensor, causing the plane to suddenly dive twice, causing some injuries on board. So you can see the effect that this actually has in the real world. But solar flares and cosmic rays aren't the only effect of the sun that can cause corruption to computer memory. Heat is another huge issue that we see in the real world, particularly with mobile devices that are exposed to the sun in the people's pockets and things like that. This can generally cause issues when writing to memory with conductivity, resistivity issues, and things like that. Google's own corporate data centers have been frequently subjected to issues of overheat with their hot aisles in their data centers coming up to 35 degrees Celsius or 95 degrees Fahrenheit. This isn't a mistake. This is a deliberate business decision by Google to say that they've calculated that the expected loss of their server systems and things like that is less than that of actually cranking up their HVAC systems. And they actually use that extra heat to heat their offices and things like that. This can also be used to escape a JVM sandbox. Again, in 2003, a researcher basically had a simple experiment where they constructed a JVM sandbox, took 2 pointers, and made them point to each other. And so there was an execution that was going bang, 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 right back and forth. That same researcher then took a giant heat lamp and applied it directly on their motherboard. Sure enough, a few hours later, that memory faltered and was able to escape the JVM sandbox. Google in 2009 calculated an average of 400 bit flips per gigabyte of RAM every month across their entire server fleet. These numbers are disputed and go up or down depending upon which vendor you actually talk about. This increases for devices under stress or higher elevations. So those plane examples I was talking to you about earlier, if you're at a plane cruising at 30,000 feet, you're 30 times more likely to experience one of these upsets. The most common way of defending against this is to use ECC, or error code correcting memory. This is effectively memory that has parity bits inside of it to basically detect and correct these errors as the execution is executed. And this can also happen in DNS requests. So if you're a client and you're going to example.com and one of these issues occur, then that 1 in the E could flip to a 0, causing you to navigate to dexample.com. And this can happen in 2 specific ways. The first is a corruption in the DNS name resolution, so the question and answer there, as you can see there. And the second is corruption of the request body content itself. So that's things like a script tag, as you can see here. Now these are 2 very different ways of interacting, because the first will simply fail in the event of a TLS or an SSL certificate. The second, as you might have guessed, uses the TLS SSL certificate of the dexample.com website. There are also a number of different types of corruptions other than this, so over the network, user typos, and a bunch of others, but they're less common. So now I get to bit squatting. Now, bit squatting is the intentional technique of registering domains that are exactly 1 bit away from your target instance. In my case, I targeted the 3 main cloud providers, AWS, Azure, and GCP, where I registered domains that were 1 bit away. This was my setup. I simply registered the domains names. I created a wildcard DNS record in Route 53, including DNS logging to CloudWatch logs. I set up a HTTPS server logging the headers, query string, request body, and everything else, but I only returned to 404. I didn't actually want to corrupt someone's workflow here. I used Let's Encrypt for the SSL certificates, and that is literally all you need to do to start receiving a subset of misdirected traffic from cloud providers to the cloud endpoints. There's one little caveat to this, and that's something you may have experienced before. The internet's full of bots. If you register a domain today and have a TLS certificate registered against it, you will receive about 500,000 requests per month, mostly from bots. And a lot of these common subdomains is the type of things you'll see. So in my research, I had to actually filter this out, which is very annoying. Let's get into an example. Let's talk about Azure. So my target for Azure was Azure.com. And here you can see all the available 1-bit bit squats that are available, that will exist for Azure.com. All the regular, non-premium domain candidates for Azure.com were taken by a variety of different clients, except for one, Azure.com, which I registered. I then created an SSL SAN that included only the star.azure.com. If you look on the right there, you can see the exact bit that I flipped for this registration. As a spoiler, during my evaluation period, I received no requests that actually contain authorization headers. My expectation for why this happened is that the Azure.com endpoints have a number of different subdomains. For example, the global.handler.control monitor Azure.com domain does not match the SSL certificate that I registered. These requests, by the way, are all requests that are received either in the HTTPS server or the DNS logs themselves. So you can see a number of requests for customer VMs, some of which were active, some not, a request for SCOM, and a whole bunch of requests for telemetry itself. In this specific telemetry example, those last 2 digits represented the product that was receiving telemetry. So that's for O365, VS Code, and things like that. Let's talk about AWS now. For AWS, I registered, here are the domains for the single bit squats for AmazonAWS.com. Now, all of these regular domain candidates were taken. In fact, they're all taken by the same exact service and IP, which was a Mark Monitor service. This means that Amazon has gone out of their way to try and defend against this specific attack. So does that mean game over for me? I have one more trick up my sleeve. Introducing Punycode. Punycode is Unicode for DNS, and it's the exact same technology that allows you to have emojis in URLs. The standard bit squatting techniques only look at those first 7 bits because that's what DNS expects. But I also considered that 8th bit. So for example, AmazonAWS.com with that accented A converts to that domain there you can see that starts with XN -- something. I registered all 9 variants of this, and this time I had SSL certificates that include star.region name, star.elb, star.execute API, S3, etc., etc. Again, I received no authorization headers in the requests that I received for this specific service, where I expected SIGv4 signed requests. My belief is that for these requests, because the SIGv4 process is so complex, it would have broken somewhere else if I hadn't had multiple bit flips concurrently stacked on top of each other. But I did see traffic. So I received traffic for S3 buckets, ELBs, again, customer VMs, API gateways, and so on. For the S3 buckets, here's a summary of some of the bucket requests that I received. So buckets like loyalty programs, digital agencies, hotel chains, shopping companies, athletics clubs, social media apps. Again, these are real buckets that exist that I've actually filtered out for the customer's privacy. But they are legitimate companies that I could positively identify, some of which you would have heard of. One of my particularly scary ones here is the payment card tokenization JavaScript download. So effectively like Stripe.js, but not Stripe.js. So this triggered fear in my PCI DSS brain. One more thing was that these MRAP endpoints, these multi-region access points, were very interesting. They are naturally obfuscated because of the way the service works. One interesting quirk in this is that every single one of these start with the letter M. That is not something I knew about the service, but I found in the data that I was capturing. Funny service quirk there. Finally, I want to talk about GCP. Here my target was googleapis.com. Again, here are all the bit squats that are available for that. And this time there were many of these regular domain candidates available. Since this research was disclosed to Google, they've actually gone ahead and registered all the available ones there. I registered to Google APIs, Fugle APIs, and my personal favorite, gongleapis.com. Again, you can see the ASCII flips there for your inconvenience. The SSL SANs only included star.whatever the domain was. And this time I found a lot of authorization headers in these requests, but not just for Google Cloud products. The googleapis.com namespace is home to many of the standard Google services, including Safe Browsing API, Google Maps, Android Backup, Play Store, Nest, etc. Let me go through some of the requests that are received for this specific services. Starting off with telemetry. I received full crash dumps that were reported by Google and a bunch of other things that may include things like mobile numbers, MAC addresses, and if they were logged into Google, their email addresses. You can see a bunch, and this was one of the most frequent requests out here, this log batch API, which happens every 6 hours on Android devices or every time you do an event such as plugging in a SIM card. My understanding is that this is not something you can easily disable in an Android device. Request for Play Stores was also in here. Again, always authorized, so you can take this authorization header and do your own activity here. This second request here actually had a full dump of all the applications, all the app IDs that were on this person's device. requests for Play Store front end, Play Movies front end, and even the endpoint that allows you to download APKs to your phone. For those who don't know, that's basically the binaries of the applications that you install on your phone device. There were requests for Firebase in here. For those who don't know, Firebase is an online database that Google Cloud provides. And these include requests to write to a specific Firebase instance or to listen to those writes from a Firebase instance. There are also requests for Google Maps. There were a lot of these, in fact. So requests for Street View, requests to get specific directions. Now, if you can think about the type of exploits that you could do when you actually try and tell someone a direction that is not from Google, and what you could do, you could cause traffic jams, you could do a whole lot of different activities. It's a fun thought experiment. And things like the My Location history, which was a constant request that basically says, here's where I am, and things of that nature. Some other ones, miscellaneous ones from Google, so YouTube player events, URL safety checks, the Chrome sync passwords endpoint, which doesn't do exactly what you think it does, but is still very scary. Requests to get data from Google Sheets, and of course requests to refresh tokens. So the last endpoint there is basically going to receive a bunch of refresh tokens and get back a bunch of access tokens for those requests. But there is one more I want to leave you with, and that's Google One Backup. Google One Backup is a service that basically allows you to back up things on your mobile devices into the cloud. But the endpoint for this is very simple. The endpoint basically expects you to send a file name, a MIME type, and the raw bytes of the thing that you're backing up. And this is obviously, again, included with all the authorization tokens and things of that nature. Now, again, those raw bytes were included in the request. And if they're images, they could be something like someone's screenshot of a contact, or rather, a photo they took of their vehicle registration, all misdirected through an anonymous endpoint. Pretty mind-blowing. So wrapping up, so here's some of the disclosure timelines for the vendors that I disclosed to. Amazon requested more details, sample data, and although they confirmed no further action, they requested a transfer of the domain names to their host master team. Microsoft immediately marked this as low priority and closed, and just didn't talk to me. Google did come back, asked for sample data, and they actually asked me to, with the tokens that were coming in, send them through the token info endpoint to get some more detail on these requests. And these were valid requests, and I could see more information, like the application that it came from. Google are, in fact, working on a resiliency fix for this. They are working to improve their client libraries to detect these bit flips by making a TLS hook to assess the X509 host name of the certificate that the client is talking to. So Google's actually working to fix this. Okay, last slide, I promise. Post-mortem, you and your organization probably don't need to worry about this, as scary as it looks. It happens so infrequently and so rarely that it is not something that a targeted attacker could use against you realistically. Devices that did connect to my high TTL domain names had a varying level of persistence between minutes and hours. For the vendors who are protecting against this with proactive domain registration, I encourage you to remember your non-primary domains. Prevalence of VCC memory and similar device mechanisms need to be considered for consumer devices, although this is a cost and expense benefit kind of trade-off. AWS have uniquely defended against some of these attacks with the SIG-v4 protocol, and I am excited to see Google working on specific client-side detection mechanisms so they can fix this in the future. And this research did nothing to help my domain name purchasing addiction. Thank you for listening to my talk.
Questions in the back, and then.
Hi, thanks. That was really cool. I just wanted to clear something up. It sounded like with the puny code that you used, it sounded like it was not 1 bit away using the puny code character, and I was surprised how much traffic you got. So I just wanted to double check, like, was all that traffic you got over a long period of time, or was it truly just 1 bit away, or?
This is long. So if you actually look closely, these traffic is actually 1 bit away. The difference is that it's not a common DNS name to have the accented A. That's not a valid DNS name. But what's actually happening is when the browser sees something like the script tag, it's going to convert that to that puny code domain. So although it doesn't look like it's 1 bit away, the 1 bit is actually translated when the customer browser or whatever is interpreting this is doing that conversion for you. So it is actually a 1-bit bit squat. It's just that there's a transformation that happens in between the time that's evaluated and the time that the request goes over DNS.
Oh, okay. Thanks so much. That's awesome.
Thanks so much, Ian. Really, really great talk. One of the questions I had, I would love to see some of the information and telemetry you have around the time to live on the conversation flows. I think that would be super interesting, seeing how many of them are minutes and how many of them are hours, just in order to see what the, what the event, how long it occurred.
Yeah, makes sense. Yeah, so the minutes to hours thing is based on my own analysis of this. It's actually quite hard to disambiguate what is a new session, I guess you could say. There is this effect, this kind of lock-on effect, where when a specific client does resolve this, they get locked on. Because I'm responding with 404s, they do tend to retry the request a lot. For some poorly coded kind of applications. So you'll see the same request going over and over and over again, getting the same 404 until it eventually gives up and then I assume tries to re-resolve DNS. Basically, it's just hard to figure that one out. It's, yeah, there's a lot of telemetry, there's a lot of logs and things like that to figure that one out.
Hi, that was an awesome talk. You're specifically targeting DNS with this. Do you think there's other protocols or other interesting areas where bit flips might happen, like maybe certificates or other things?
Yes. The story that Ben Kehoe told me, and I don't want to repeat it here because it's his story, did involve DNS. This does happen with other resources that might not necessarily be DNS, so you can think about things like unique identifiers, right? This can happen basically anywhere and any time, although it's more likely to happen, again, in a client-side device, which doesn't have that ECC memory protection. But we have seen it happen in other things, like the voting booths or things like that. But DNS was the specific target I wanted to use here because I could, in fact, capture a subset of cloud traffic.
Thanks again. Great talk.
Thank you.
I was wondering if you found any patterns in terms of geolocation for the requests. Like, were there any hotspots?
Yes, in fact. How do I say this without offending a lot of people? There was a lot of Middle East-looking map requests, and I assume that was due to the heat that was actually available in those locations. That was a common occurrence. I did see 1 or 2 from the US, and that's probably just due to the population frequency and the prevalence of the use of those type of requests. But yeah, by far and large, it was kind of Middle Eastern style locations where I assume the device would be overly affected by heat and things like that.
So sticking to host names, the bit flip would have had to happen before the encryption happens of any sort.
Yeah.
And so I don't see why this could not have happened with SIG-v4. Before the HMACs happen, if the bit would flip, it's the same as your script tag.
Yes, but so there's 2 things that are happening here. One is that the DNS or the destination flips, and the other is that the signing needs to happen. I believe what's happening there is that the SIG-v4 process has a lot of internal things around the DNS about what actually happens there, and if that doesn't actually match to the original DNS that it expects or to the actual expected service host name of the service that's being signed, because it's looking in its own data set for how to sign that service, it's going to cause a corruption in that space. And I believe that's why that's happening.
Thank you, everyone. One more round of applause for Ian.